Do you know how to sketch sketches using not so sketchy control methods? Our goal is to draw any image using two motors. To do this, we would need to control the motors for each x and y axis. This ODE is the motor equation. We can change the input or the voltage to control the output or the angular velocity of our DC motor. We can also call the output as the response of our motor. We can represent this as a block diagram, as shown in the picture on the top. This is called open loop control, where we are supplying the voltage to the motor blindly. However, we need to stop applying the voltage to the motor at our desired position so that the motor stops rotating. We can optimize the various voltage input of the controller analytically to turn the motor in our desired way, but this is only possible when our system can be modeled perfectly, which is basically impossible. In other words, we need a numerical way to vary the input of the motor based on the output. Thus, we should make a loop where the output affects the input voltage. We can represent this as a block diagram again, as shown on the bottom image. This is a closed loop control block diagram. We can see that the output of the motor is compared to its desired value and the voltage supplied according to the difference between the two. The difference between the output and the desired position is error, and the according to part mentioned before is actually another function, a function with the input as the error and the output as voltage. We call this function a controller because this is what controls our input, which in turn affects our output.
We need to have information about the motor trajectory that will draw the eagle. First, we will extrapolate the trajectory from the bitmap image. We will control two motors using PID control and another control. We will analyze the results of two control methods. We will use the contour error as the main performance criteria as drawing the eagle accurately.
Most bitmap image formats we use, such as JPG or PNG, do not have time information. So let's convert this bitmap image to a vector image, such as SVG, and obtain the desired motor trajectory. How did we vectorize the image? We first decompose the original bitmap image into a subsequence of pixels, which are used to create a group of paths, creating a polygon. Then we will turn these polygons into parametric curves in the form of Bezier curves using vertex adjustment. Finally, the curves are optimized by comparing segments of adjacent Bezier curves and merging similar ones. Bezier curve refers to n-1 order parametric equation obtained from n points. The picture on the top left and the video on the right are third-order Bezier curves using 4 dots. In general, most curves can be expressed through a third-order Bezier curve. We can use an open source program that extracts parametric equation from our SVG file. By substituting values into this parametric equation, we wrote Python code to convert a continuous curve into discrete points for the motor to move to. Plotting the coordinates using Python's matplotlib library confirms that we have successfully created a valid trajectory which will draw our image.
To physically move the motor to desired positions, we will use PID control. To implement PID control, it is necessary to utilize the derivative and the integral of the error. We use the backward difference and rectangle method to calculate these with minimal computational cost. This will increase our iteration frequency and will have a noticeable improvement in control performance. How do the gains actually affect the response characteristic of our motors? These three graphs shows P control, PD control, PID control. Target position is 5 for all control. For P control, input to the motor is error multiplied by P gain. By P control, input voltage of motor is proportional to the error. As you can see in this graph, there is overshoot. To reduce overshoot, we use D control. For D control, input to the motor is discrete derivative of error multiplied by D gain. With D control, we can reduce overshoot and also settling time. Settling time means duration it takes for a system to reach and remain within a specified range of a target. But with P and D control, we can reduce steady-state error. To reduce steady-state error, we use I control. For I control, input to the motor is discrete integral of error multiplied by I gain.
While we haven't shown you the results yet, even with a well-tuned PID controller, we are faced with a conundrum. If the motor is too conservative at moving towards the desired set points or reference positions, we would have to increase the proportional or integral gains. However, doing so will increase oscillations or overshoot, because now the sensitivity to disturbances have increased as well. This will cause our sketcher to draw squiggly lines. So we need a way to tune the controller such that it compensates the disturbances aggressively, but doesn't approach the set points too aggressively and cause overshoots and oscillations. From our single loop PID controller, let's zoom in on the plant, or the motor block. The voltage output of the controller UT is the input to the plant, and the resulting position of the motor YT is the output. Now we can see that this part is just another open loop system. And what have we learned so far is that we can improve the performance of open loop systems with closed loop systems. So let's add another PID controller to this open loop. Now we have two PID controllers with the output of the inner loop affecting the input of the inner loop and the output of the outer loop affecting the input of the inner loop. These PID control loops are cascaded, hence the name Cascade PID control. We have also separated the sources of disturbances. Disturbance D2 in the image would be high frequency disturbances, such as disturbances arising from the DC motor, friction in the gears, etc. Disturbance D1 are relatively low frequency disturbances, mostly external disturbances, such as someone grabbing on the motor shaft. In order to separate the disturbances effectively, we would need to have the inner loop iterating at a much higher frequency than the outer loop, so that the inner closed loop system appears as a single block to the outer loop, as we had in the single PID control loop before. By setting the inner loop PID loop aggressively and the outer PID loop conservatively, we can improve the performance of our system.
If we draw a picture by trajectory made by SVG file, the result is shown here. When actually drawing a picture, just like lifting a pencil between a gap between lines, the same approach should be taken when drawing with a motor. It is essential to recognize the jump between lines, where lines are not connected. We get x and y trajectory with function generated by SVG file. We made a flag called sJump, and if this value is 1, we regard this part jump and stop recording motor's position.
We estimated the accuracy of each drawing based on distance between motor's location and closest target trajectory. As the drawing is not dependent with respect to time, we reasoned that calculating error without using time is reasonable for computing drawing's accuracy. This is a suitable performance criteria to estimate the effectiveness of the PID control method. These are the motor's drawings using different types of numerical control. Left drawing is drawn with PID control, and the right drawing is drawn with cascade PID control. As the control error scale is small compared to the entire drawing, it's difficult to recognize the difference. Now it shows the error value of each drawing. Left one has an error value of 0.01889 and right one has the value of 0.01827. Cascade drawing has smaller error than PID drawing. It shows that cascade is more delicate than PID.
For our system, we have a so-called cascade PID controller. Since we want our system to react and respond to disturbances, we use a closed-loop PID to give an appropriate voltage to the motor. However, we have added another PID loop to separate disturbances from various sources. The second closed loop uses the velocity of the motor to change the input voltage, which affects the feedback of the outer loop. We have two closed-loop PID controllers in the same system. By literally taking a closer look at our diagram, we were able to think of a more advanced method of control with the same principles. This control method allows us to reach our desired positions much faster than the single PID control method without the risk of oscillations or divergence.
During this 8-minute demonstration, we have shown that we can turn any image into sets of parametric equations, and we can improve controller performance by separating disturbances based on their frequency. We can also improve the time complexity of our error calculation algorithm from O of n squared to O of n log n by comparing the motor positions to their respective parametric lines. This alternative algorithm is an exercise left to you, the viewers.